Organic Chemistry, Chem 212, Exam 5 Material, Part 1. Structure determination using mass spec and infrared spectroscopy. Determining the structure of an organic compound. The analysis of the outcome of a reaction requires that we know the full structure of products as well as the reactants. In the 19th and early 20th centuries, strategies were determined by synthesis and chemical degradation that related compounds to each other. Physical methods now permit structures to be determined directly. We will examine mass spectrometry, also known as MS, infrared spectroscopy, IR, nuclear magnetic resonance spectroscopy, also known as NMR, and we're going to look at both proton NMR and carbon NMR. And lastly, ultraviolet visible spectroscopy, known as UV-Vis. Mass spectrometry, MS. This measures the molecular weight of our compound. The sample is vaporized and subjected to bombardment by electrons that move an electron, and this creates a cation radical. Bonds in cation radicals begin to break down or fragment, and we're able to measure the mass-to-charge ratio. We have our organic molecule, it's bombarded with an electron, the cation radical is formed, and it's this cation radical that we detect in mass spectrometry. The mass spectrometer. Molecules are ionized by collision with high-energy electrons, causing some of the molecules to fragment. Passage of the charged fragments through a magnetic field then sorts them according to their mass. The sample comes in, and it becomes ionized. When it becomes ionized, it gets hit by a whole bunch of electrons, and then it's going to fragment into different pieces, and each piece is going to weigh differently. And as it passes through the magnet, so when they come out, we're able to see the differences in masses. The mass spectrum. It's a plot of the ions, M over Z, along the x-axis, versus the intensity of the signal. This roughly corresponds to the number of ions, and that's going to be on the y-axis. Taking a look at the spectrum here, we have relative abundance. On an MS, the top number is always 100. And whatever ion we have at the highest concentration, we're going to go ahead and mark that as 100, and the rest are relative to it. So we can get an idea of the different percentages. The tallest peak, in this case, right here at, we'll go ahead and call this about 39. This is going to be known as my base peak. All other peaks are listed as a percentage of this peak. The peak that corresponds to the unfragmented radical is called the parent peak, or the molecular ion, known as M+. In this case, we have a series of peaks at the highest molar mass up here, the mass-to-charge ratio, or molar mass here. When you have a series of them, typically the highest of the last grouping would be your parent peak. In this case, my parent peak is at 44. Here's an example of MS using methane. Methane produces a parent peak at a mass-to-charge ratio of 16, and there are fragments at 15 and 14. The tallest peak is our base peak, and in this case, our base peak is also our parent peak. The parent peak is the tallest one in the last grouping if there's more than one. The mass-to-charge ratio of 16. Here is what happens during the bombardment. Methane is bombarded with electrons. We get a molecular ion out of this where it loses one electron. We now have a positive charge here. And then these can fragment even smaller, where we can get a mass-to-charge ratio of 15 where a hydrogen is removed. And another common peak or another common fragment would be a mass-to-charge ratio of 14 where 2 hydrogens were lost. Interpreting mass spectra. Peaks above the molecular weight appear as a result of naturally occurring heavier isotopes in the sample. In the spectra here, I went ahead and just took the one from the methane before and cut it off, just looking at this piece here. Take a look at just one above the parent peak. Remember, this was the parent peak here. Just one above it, we have this little tiny line right here. That's known as an M+1 peak. And this comes from the fact that we know that carbon-13 is randomly present. Its percentage is 1.1%. We can almost see that this small line here is almost 1% of our total line. We also have an M+1 peak present when we have nitrogen. Again, it'll be a small peak just like the other one, 1.38%. The M+2 peak is also a great way for us to determine whether or not we have a bromine or chlorine present. In fact, the ratio we have of bromine is always going to be a 1-to-1 ratio where you have two peaks towards the top. Right here, let's take a look. We have a 170 and a 172. Do you see how both of these are really far down? They're going to be our parent peaks. One of them is going to be our parent peak. Well, the 170 is going to be our parent peak, and our 172 is going to be our M+2 peak. And that's because we have nearly a 1-to-1 ratio of the 2 molar masses of the most common isotopes. Now, chlorine will give us 2 peaks, also really high up there where the parent peak, one will be the parent peak, but in that case, it's a 3-to-1 ratio. What we know from this spectra is this happens to have bromine in it because we have peaks at 170 and 172 where we have an M parent peak and we also an M+2 peak, almost identical heights. Sometimes we'll get peaks that are below the molecular weight, and this is a result of something that's left, and a very common example would be hydrogen leaving an alcohol group. In this case, we have an example of an 87, which would be the M-1 peak. Another thing we can get in interpreting mass spec is if our molecular ion value is an odd number, that tells us we have an odd number of nitrogen atoms present. Interpreting mass spectra using fragment patterns. The way molecular ions break down can produce characteristic fragments that can help in identification. This serves as a fingerprint for comparison with known materials in analysis and commonly used in forensic science. The positive charge goes to the fragment that can best stabilize it. This molecule here, so we have our parent, so this would be our molecular ion. It can undergo another fragmentation, and what it did in this case is it lost a CH3 group. Of these two pieces here, the only one that can be detected in mass spec is the one with the positive charge. Only positive species show up on a mass spec. So what you would see, for example, is you would have your parent peak, your mass to charge ratio with this molar mass, and you would see another peak at 57. And what we would notice is between here and here, we had a loss of 1 carbon and 3 hydrogens. Well, carbon weighs 12, hydrogens weigh 3, so that means we would have loss of a minus 15 in terms of molar mass. We commonly see methyl groups fragmenting off, but we don't see their peaks. We see the result of it being removed. So many times we will see a minus 15, and that tells us we had a methyl group. That tells us a little bit about its structure. Mass spectral fragmentation of hexane. Here we have hexane. It has a mass to charge ratio of 86 for the parent chain, and we see some peaks at 71, 57, 43, and 29. And we do see more peaks on there. We're not going to be able to identify all the peaks, but sometimes we can get some information from a few of them. I went ahead and marked up the spectrum here. First of all, this M+, this is going to be our parent peak right here. That is at 86. So what that does is that tells me that the molar mass of the compound is 86. So let's say I didn't know this was hexane. One thing I could do from the mass spec is now that I know that the molar mass is 86, and if I know it's hydrocarbons, what I could do is I could take 86 and divide it by 12. I divide it by 12 because that's the molar mass of carbon, and when I do that, I can get an estimate for the number of carbons in this compound. Another thing that I marked on here is the base peak. That's the highest peak at 100. And then something that I noticed is I have a couple of fragment losses here. I have a peak here at 71. And mathematically, the difference between 86 and 71 is a minus 15. That means I lost a methyl group, a CH3 group. I also noticed another peak, and that's our base peak. The difference between our parent peak and our base peak is 29. A loss of 29 is the loss of an ethyl group, because that's the molar mass of an ethyl group. So this mass spec, not only does it tell me how many carbons, or gives me an idea of how many carbons are in there from its molar mass, but I can also get an idea of somewhat what the compound looked like. I know there's going to be a CH3 group, but there's also going to be some sort of an ethyl-looking group in there. And that's exactly what we have with our hexane. If you can see right up here, we have two CH3 groups. It's a symmetrical molecule. We also have CH3 groups. So some of the fragments are when two carbons have been removed, and another fragment is when one carbon's been removed. Another important piece of information we can get from a mass spec is when we have an alcohol undergoes an alpha cleavage. Alpha cleavage, this would be the bond one away from the carbon that has the alcohol piece. So this right here is considered the alpha carbon, one away from this carbon what's attached to the alcohol. Well, when the molecule is put into the mass spectrometer, the bombardment of electrons is so hard that not only does it break it up into fragments, but it can also break this molecule up. And we can have a common fragment when you have an alcohol would be a breakage right here, a cleavage right here. So underneath the alpha cleavage, we will see a loss of this group here. We will have a fragment of the alcohol piece still. That will have the positive charge. So the only piece that can be detected in our mass spec is the one with the positive charge. So we'll see a peak with this molar mass, but we will see a loss of this molar mass. And that helps us determine the structure. A second thing that happens to alcohols during this mass spectrum process where it's being bombarded with electrons is a reaction can happen. This hydrogen, along with this OH on our alcohol, so this hydrogen is on an adjacent carbon to the carbon that has the OH on it, it can undergo a dehydration reaction. This is also an elimination reaction. And again, the only product we see as an actual peak is the positive one in a mass spec. So in this case, we'll see a loss, and the loss will be minus 18 because that's the molar mass of water. Not only do alcohols undergo these kind of reactions in these predicted fragments, same thing with amines. Amines undergo alpha cleavage, generating radicals. So this is my alpha carbon. It's the carbon next door to the one that has the nitrogen. Alpha cleavage happens, and what gets detected is this fragment right here. It's only the positive one that gets detected. So I will see a loss in molar mass between the peaks of this molar mass. Again, helping me with determining the molecule structure. Fragmentation of ketones and aldehydes. First, we're going to look at the McLafferty rearrangement. When we have a carbon and hydrogen that is 3 atoms away, it can lead to an internal transfer of a proton to the carbonyl group. A McLafferty rearrangement causes an alkene and also an enol. Let's take a look. Here's our carbonyl group. 1, 2, 3 carbons away. I have my hydrogen right here. This is telling me, because I have a curved arrow, that the pair of electrons that are between this carbon and hydrogen are going to be given to this carbon-carbon here, giving a carbon-carbon double bond. The pair of electrons that were here are going to go here, forming a carbon-carbon double bond, and that's shown in blue over here. And then the pair of electrons that were here are actually going to grab this hydrogen, and that's going to make an alcohol piece here, an OH. What happens in a McLafferty rearrangement is we actually get these 2 carbons here become severed. These 2 carbons become this alkene. This alkene does not have a positive charge, so we won't see a peak in mass spec. But this piece, this rearrangement piece, is charged, so we will see a peak here. So this would be the molar mass loss that we would see here, again helping us with the identity of the compound. So we saw alcohols undergoing an alpha cleavage. We saw amines undergoing an alpha cleavage. We can also see an alpha cleavage with other carbonyl compounds. This is the carbonyl group here, the carbon involved in that. One away is the alpha position. Alpha cleavage, we're going to have it break right here. And this will be the loss. So we'll see not a peak here, but a difference of this molar mass. And it's this piece right here, the one that's charged, that we'll see a peak in our mass spec. Now we're going to look at spectroscopy of the electromagnetic spectrum. Radiant energy is proportional to its frequency, and we look at this as cycles in hertz. And if we look at it as a wave, we look at the amplitude and its height. There are different kinds of electromagnetic energy, and we can look at them either by frequency or wavelength. Here we have energy increases as we go from right to left. So we have gamma rays being the highest energy, radio waves being the lowest energy. And right here in the middle of this, we can see this white piece here, and we've expanded it out here because it's really not that much of the spectrum. This is known as the visible spectrum. This is what our eyes are tuned in for, that we can see. So our eyes are a detector of electromagnetic waves, but the only waves we can see are in these frequencies here. Now there's other frequencies just to the left and just to the right of them. We have ultraviolet, a little higher frequency than we have in our visible range, and we have infrared, a little bit lower in energy. We can't see any of these other waves, but we can have other things that can detect them. Absorption spectra. Organic compounds exposed to electromagnetic radiation can absorb energy of only certain wavelengths. Changing the wavelengths to determine which are absorbed and which are transmitted produces an absorption spectrum. Energy absorbed is distributed internally in a distinct and reproducible way. Each downward spike corresponds to an energy absorption. This example is ethyl alcohol. So what we're talking about, the downward spike, right down here where it comes down, this is where we're talking about the energy absorption. And we're going to find when we have an IR absorption that we have some characteristic peaks, well, basically valleys. We have to look at this upside down. We'll have some characteristic spaces that'll show us something. Now, alcohol, ethyl alcohol structure has 2 carbons and 1 OH group. In our ethyl alcohol, CH3CH2OH, it's this piece right here that we're going to find in this region of our IR spectrum. Very characteristics of an alcohol. The main reason why we use IR and its main purpose and use is to verify that we have certain functional groups there, or to let us know that certain functional groups are not present. IR energy in a spectrum is measured as a wave number, the inverse of the wavelength, and proportional to its frequency. So across the bottom here, we start off with 400. This is its wave number. We have 1,000 here. And then I want you to notice that once we get past this 1,000, that it's no longer the same distances for the units. We have 200 between here and here, whereas it's this distance here that gives us 200. So that's also another thing that happens on the IR spectrum. So typically on IR spectrums, they'll give you a range at which you're going to find these peaks. Where the energy comes from, where does the absorption come from? In IR, energy absorption corresponds to specific modes. They correspond to a combination of different atomic movements, such as bending and stretching of the bonds between the different groups of atoms called normal modes. Energy is characteristic of the atoms in the group and their bonding. The different types of vibrations and bending you will see that allows for the absorbance in IR. Symmetric stretching is when both of these bonds are going out and in at the same time. Asymmetric stretching would be the situation where one side's going out while the other one's going in, and one side's going out while the other one goes in. There's also in-plane bending, where instead of stretching, what they're doing is they're bending back and forth. And we also have out-of-plane bending. As we mentioned earlier, there's going to be a range at where we're going to be seeing the different absorptions. So this is a nice little table here that tells us if we have a carbon double bond oxygen, a carbon double bond nitrogen, or a carbon double bond carbon, we'll normally see the absorption in this range here, somewhere between 1,500 and 2,000. For a carbon triple bond nitrogen, or a carbon triple bond carbon, that range is about 2,000 to about 2,500. And then we'll see a nitrogen-hydrogen bend and stretch, oxygen-hydrogen bend and stretch, and carbon-hydrogen bend and stretch in this range here above 2,600. Anything below about 1400 is known as the fingerprint region, and that's where we can really get some identification of specific compounds in there. Now the functional groups pretty much all are above 1500, but these different peaks down here in the fingerprint region can also give us some information. Chromatography purifying organic compounds. In order for us to have our compound undergo a mass spec or an IR or any of these other spectroscopies, we want to have a pure compound. So one way we can get a pure compound is through the process of chromatography. And what this does is it separates compounds using adsorption and elution. The mixture is dissolved in a solvent, also known as the mobile phase, and placed into a glass column of adsorbent material. That would be the stationary phase. Solvent or mixtures of solvents are passed through. Compounds adsorb to different extents and deabsorb differently in response to appropriate solvent. This is known as elution. So if you have a compound that prefers the stationary phase, that's something that's going to hold on to that stationary phase, and it's going to stay put in the column longer than something that likes the mobile phase or has an affinity to the mobile phase. And something that likes the mobile phase and grabs onto the mobile phase is going to flow through the column quicker. And that's the idea behind separating these. The purified sample in solvent is collected at the end of the column, and you can change out the container when the new stuff comes through. This can be done in a liquid or gas mobile phase. The principles of liquid chromatography is the stationary phase can be an alumina or a silica gel. Solvents of increasing polarity are used to elute more and more strongly absorb species. Polar species absorb more strongly to the stationary phase. For example, alcohols absorb more strongly than alkenes. In this case, we have our gas that's going to go ahead and help our samples flow through. We inject our sample. The column is fairly long because we want to have time for the separation to occur. Remember, the ones that like the mobile phase are going to move faster. The ones that like the stationary phase are going to move slower because they're going to hold on to that stationary phase a little bit longer. And then what happens is it comes out to the detector. We can go ahead and then get a reading. The first stuff that comes out like the mobile phase better, and the second stuff that comes out likes the stationary phase better. We can do separations, in this case, using charges, using polarity. High pressure or high performance liquid chromatography, HPLC. This is a more efficient and complete separation than ordinary liquid chromatography. In this case, we have coated silica spheres. They're about 10 to 25 micrometers in diameter, and they're in our stationary phase. High pressure pumps force solvent through a tightly packed HPLC column. The detector monitors the eluting material. Here is an HPLC analysis of a mixture of 14 different pesticides, and the mobile phase was an acetonitrile water mixture. All of these 14 different pieces have been identified on this spectra.